All right, so in this section, we're going to talk about proofs with perpendicular lines. Now, the distance, anytime we measure from a point to a line, it is the length of the perpendicular segment from the point to the line. The length of this segment is the shortest distance between the point and the line. So here we have point A, and down here we have line K. And we want to know how far it is from B to K. So we're going to measure from A straight down to B at a perpendicular angle. And this is the distance from a point to a line. And the reason we do it this way, it's the shortest distance, and it's a consistent distance. If we know if we're measuring to the perpendicular, we're measuring the same way every single time. So let's recall our distance formula. So we have x2 minus x1 squared plus y2 minus y1 squared. We plug in our points, we find the distance from the line to a point. So find distance from point A, this guy right here, to line BD. BD is right here. So we got three options. We could measure to AB. We could measure to AD, or we could measure to AC. Well, only one of them is a perpendicular to the line, so we're going to cross off these other two because they're not what we want, and we're going to measure AC because that's the true distance. So we're going to plug point A and point C into our handy-dandy distance formula, and we're going to go 1 minus a minus 3 squared plus a negative 1 minus 3 squared. So that's going to be plus 3, so that's 4 squared. 1 minus minus 3, that is a negative 4 squared, still inside the radical. So that's radical 32, which reduces down to 4 radical 2. Or if we put in our calculator, it's going to be about 5.7 units. Now let's look at another example. Once again, we want to go from point A to line BC. Here's B, here's C. And once again, we need to measure that right here at the perpendicular. So we are going to find ourselves AD. Fortunately, we have the distance formula that'll do that for us. So minus 4 minus a minus 1 squared, quantity squared, 2 minus 8 squared, going to be negative 3 squared plus 6 squared. So that's a radical 45. So we can reduce this down to 3 radical 5, or we can put in the calculator and get about 6.7 units. All right, so let's do one more together, and then you can try some on your own. So let's find the distance from point E to line FH. Well, we recall that we always measure to perpendicular. Perpendicular means we create a right angle. So EG is what we're looking for. And we get 1 minus a minus 4 squared plus 2 minus a minus 3 squared. So it's going to 5 squared plus 5 squared radical 50. Which is 5 radical 2, which is the exact answer, or we can get about 7.1. So pause the video, answer this question, which is different, then hit play, and we'll see how you did. Well, let's look. The distance from point X to line YZ. So distance from line X, from point X to line Y to WZ. Here's Z up here, so here's WZ. We're going to measure this at the perpendicular, so that's that right there. Find XZ. XZ is going to be this one right here. Okay. Find the length of XY. Well, XY is right here. So now we got 2 pink ones and 1 green one. Find the distance from line L. And here we named it line L to point X. So which one is different? That'd be this guy right here. It's the only one not finding us the distance of XY. So let's use the diagram above, which is this right here, to find XZ. Oh, okay. That's just the distance formula. XZ is one we highlighted in green originally, so let's just find that using our distance formula. No problem at all. We know how to do that. So we get 7 squared plus 1 squared. We get 49 plus 1. So that's radical 50. So an exact answer reduced to be 5 radical 2. Or if we put in our calculator, we'd get 7.1. About 7.1 units. Now we want to find WZ. Well, WZ is right here. So we're just using our distance formula again. So let's go ahead and plug it in. So we get 2 minus 4 plus negative 2 minus 4. So we get negative 2 squared plus negative 6 squared. So that's 4 plus 36. That's going to reduce down to 2 radical 10, or about 6.3 units. Same distance formula we've done before. And we always measure from a point to a line at the perpendicular. Which brings us to our linear pair perpendicular theorem, which tells us if two lines intersect to form a linear pair, which as we recall is two angles that create a line, a pair that creates a line. But if we have a linear pair of congruent angles, then the lines are perpendicular. So that means if angle 1 is congruent to angle 2, they're a linear pair, they equal 180, so they each have to be the same and add up to 180. So that means both angles are 90 degrees. Both angles are 90 degrees. It means line G and line H are perpendicular. So then G is perpendicular to line H. Simple enough if you think it through. So perpendicular transversal theorem. In a plane, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other line. So here we have our little arrows that tell us H and K are parallel. So let's write that down. If H is parallel to K and J is perpendicular to H, which is what the little box means on H, then J is perpendicular to K. So this will also be true. All right, so if this is true, and let me go back to red for my little box here and here, which has to be true. Brings us to the last one, lines perpendicular to a transversal. In a plane, if two lines are perpendicular to the same line, which we have right here, then they are parallel to each other. So if M is perpendicular to P and N is perpendicular to P, then M is parallel to line N. And once we start looking at the slopes, we'll see that that absolutely has to be true. In fact, let's go ahead and prove the perpendicular transversal theorem. This one right here. That's what we're going to prove. All right, so we're given that H is parallel to K and J is perpendicular to H. So we know that these things are true. And we know the measure of angle 2 equals 90 degrees, because the definition of perpendicular lines. We know the measure of angle 2, we know that angle 2 is congruent to angle 6 because of corresponding angles theorem. So if they're congruent, then their measure of 2 equals the measure of angle 6, because that's just the definition of congruent angles. So the measure of angle 6 equals 90 degrees. That's just the transitive property of 2 equals 90. The measure of 2 equals 90. And the measure of 2 equals the measure of 6. And the measure of 6 has to equal 90. And J is perpendicular to line K, because that's true. And again, that's just the definition. Perpendicular lines. So the perpendicular transversal theorem, we now know, has to be true. All right, the diagram shows the layout of walking paths in town park. Determine which lines, if any, must be parallel in the diagram. Well, we just talked a lot about perpendicular lines. And here we have 2 lines perpendicular to the same line. That sounds familiar to me. In a plane, if 2 lines are perpendicular to the same line, then they are parallel to each other. So A is parallel to B. Why? Because lines A and B are both perpendicular to D. So by lines perpendicular to a transversal theorem, they are parallel. All right, so we're going to use this diagram here to answer both of these questions. In fact, pause the video, you answer these questions, and start up again, and we'll see how you did on the other side. All right, so is B right here parallel to A? Yes. Why? Because A is perpendicular to D and B is perpendicular to D. So by the lines perpendicular to a transversal theorem, A is parallel to B. is B perpendicular to C? Yes. Because B is perpendicular to D, and C is parallel to D. And how do we know that? Well, C and D are perpendicular to the same transversal, so they're parallel. And if B is perpendicular to D, it has to be perpendicular to C. So B is perpendicular to C by the perpendicular transversal theorem. And we are done.